Hey, welcome back to this miniature world. Today we have to make a bunch of these small parts out of Torlon, which is PAI plastic, a high-end plastic that has a high temperature resistance, for example, and high chemical resistance, I think. It's rather expensive. I bought this 300mm long stick, 20mm in diameter, and that stick was, I think, close to 300 euros. So it's fun material. Machine's quite nice. So we have to make these. If you have seen Rick and Morty, this is called a plumb bus. So we have to make these, and they're not very complicated. There are like a round disc with a hole in it. There is another hole going in from the back, not in this part yet, but there is one tricky feature, and that's this long shaft here. This is 1.6mm diameter and 9mm long. And how do you machine this? My first idea was to cut this part laying flat, leaving this square and oversized, and then grabbing it upright in the vise of the milling machine and use the boring head to OD turn this diameter. Didn't work at all. It's way too soft, especially since hey, there's a second one. Since the real part will have a 0.5mm key slot cut into it too. And that took out some more stiffness. So that route didn't lead anywhere. My next try was to make what the watchmakers call a rose cutter. And a rose cutter is basically the machinists know this as a rotary broach. You would put this in, for example, a mag drill and drill large holes, and you only machine a ring of material and leave a slug. And that's what a rose cutter like this does. It has a hole through the center. It has 4 cutting flutes, minus 1 because it snapped. And then you can just plunge in and create this diameter. And since the cutter supports the material all around, we have way less problems with deflection here. So this is a very crude version of such a drill. I just turned the ID and OD on the lathe out of silver steel or drill rod, hardened it, and then used the NSK die grinder and ground 4 cutting edges into it. You can see here with cutting disc, just sliced them in. And I didn't even anneal it. I left it glass hard, which was a mistake because, well, packed up with chips and snapped after a few tries. But this test tool told me what I needed to know. This was 10 minutes of testing spent wisely. So now we need to make another one of these, a little bit more focused on quality. Also, the heat treating will be a little bit better, and we'll make it longer and just nicer. I think we're going to turn it, then harden the front end here, and then directly cut the cutting flutes on the grinder into the hardened stock. We're not going to soft machine it and then grind it after hardening. That's a waste of time on such a small tool. And then I will also show you how I machine one of these. We're not going through all of it. It's the remaining of it. It's just small tools and careful machining. So let's go to the lathe and prepare these blanks. I want to make 2 of them since I'm setting everything up. It doesn't take up much longer. So I have some 4mm 12210 drill rod in here. I'm picking up the end of the stock with my cutoff tool, moving in 30mm to get my length. I'm putting it off directly to length. This is not a high precision dimension here. Spot drilling. And now we clear the back of the cutter out with a larger drill. This will make sense in a second. We're drilling fairly deep, like 28 millimeters, and leaving a very short end of the material on this cutter blank standing in front. As usual, when drilling with the carriage, this gives me the ability to clear out the drill very fast for deep hole drilling. Countersink just to deburr the end of the bore. And a file to break the edge. So this is now the back side of this tool. Let's get this out. We drilled not through. Since the pin we want to machine with this rose cutter is 1.6 millimeter diameter, we need a hole with 1.6 millimeter from this end in. We don't drill all the way through with 1.6 because that would create an awful lot of friction on the pin we want to create with this cutter. So flip it around end for end. Take our spotting drill. Then we take a 1.5 millimeter to rough out the majority of the material. Okay, that was roughing. Now we take a 1.6 millimeter, a new drill. I have a good stub length drill. This is coated high-speed steel. There we go. Now we make 3 more of these blanks, then we harden them and put them on the grinder. Time to harden our cutter blanks. I already hardened and ground one, just so I know my process works, and you see the condensed down version here on YouTube, of course. So I have some oil in here. This is just cutting oil. This is what I had on hand, and it's not a mineral oil, so it doesn't stink as crazy bad as if you used motor oil for quenching. Propane torch is enough for such a small part for hardening. And we're doing only the end of the part, not the whole shank. We want to minimize runout and warpage from hardening. That's also the reason why we're going to try to quench it as square and vertical as possible. That also helps to minimize warping. So you go for a nice cherry red, which is very hard to judge, to be honest. There is also the trick with the magnet, where you check with a magnet once you reach the Curie point of the metal, but I never found that really to be necessary when hardening small tools like this. Yes, you can also do things against scaling, but also again, we're grinding the whole contour of this tool anyways. So this is good, and quench. There we go, one done. And here's the second one. Oxy-fueled would be way faster, but I don't have the oxygen bottle hooked up right now. Okay, there we go. We're getting to temperature. And quench. These are now glass hard. I'm not going to put them under the hardness test because I don't want diamond indentations on them. But we can check with a regular file here, with needle file. And that's hard. Drill rod is one of the easiest to harden tool steels. The steel is now fully hardened. This is the maximum hardness the steel will get with this type of quench. But also there is a ton of stresses in them, and this is very much prone to cracking. We'll draw them back a little bit to like a straw color. Means we polish the outside of the shank, and then we take the flame to it again. Let the heat creep up towards the cutting end, and once the cutting end is about a straw yellow, we will quench it again to stop the thermal process in the material. So let's go to the lathe, use some lapping film, polish these down, and draw them back to a reasonable hardness. They will still be around 59 to 60 Rockwell C probably. Also, we're only cutting plastic with these, so not a big deal. Despite it being plastic, I want them to be hardened because the Torlon we are cutting here is kind of an abrasive plastic, even without any fillers like glass or carbon fibers. Time for annealing. I will use a smaller propane torch and I will heat the center of the part. I already did one because I forgot to turn on the camera. And I will let the heat or the color the steel gets creep up to the cutting end, which is this side. And once I get a little bit of a yellow up here, I will drop it into my oil. It's, by the way, very clever to use a paper cup for heat treating, because if the oil catches fire, you have the paper cup burning too, and that serves the advantage that you don't have to clean up after yourself. So we got some color out here, and we get some yellow here, and we drop it for stopping the annealing. There we go, 2 oily parts. And we do that strictly to get rid of some of the stresses in the material and make them not infernally brittle. So these are out of the oil, and when we take a file to them, they are still glass hard, but they're not infernally brittle and prone to explode in your face anymore when you use them. So that's a win. For when you make cutting tools, you have several choices in steels. You have your regular tool steels like A2, D2, O1, O2, W1, W2. basic oil, air, or water quenching steels, which are basically cold working steels. They do not like heat. They will lose their they will lose their temper, like some people, under heat, and become very soft, just like people. Then there are high-speed steels, high-speed steel with cobalt. These are hot working steels basically. They will hold their hardness even under heat influence. If you have for example, high-speed steel with 8 or 12% cobalt, it will still be hard when it gets a blue color on the cutting edge. And then there is, of course, carbide, which doesn't care at all, and diamond, and cubic boron nitride, and ceramics, and cermets, and there are so many cutting-edge materials. It's not even funny anymore. Powder metallurgic steels, or another one, and there are combination steel matrix materials, blah blah blah, whatever. I have no clue. So these are basic, very basic tool steels. This is also what you would use to make, for example, simple punch tooling. Very nice steel. I like drill rod, or as the Brits call it, silver steel, or as we call it in Germany, Silberstahl. 12210. It comes as centerless ground bar, is usually relatively round within the reasons of centerless grinding, and machines nicely, and it's stupid easy to harden. Here we are in CAD, and as you can see, there's a part modeled up. I removed some features that you don't need to see, and I have the drill that we're going to make here. And when we look in the cross section, you can see that the tool wraps around this round section of the part we're machining, but it touches it only here on the last 2 millimeters. I relieved the back here to keep the friction against the shank to a minimum and not twist and rip it off the actual part. There is also no relief, no back relief in this bore. It's just a straight through bore with a relatively short contact length, and I figured that might work in this case. So let's look how the flute geometry comes together. Let's turn up the section view, remove the part, and look at this geometry. This is the cutting edge, and everything behind it is just the gullet where the chip goes. And this geometry is created by having a grinding wheel. Whoop, that's a very large grinding wheel. That's a 100 millimeter diameter grinding wheel. That's the one that I'm using on the TNC grinder. And we're just plunging in from the side. Due to the large radius of the grinding wheel, it almost appears to be a flat surface here. We create the cutting edge up here, and we also create the next cutting edge over here. And this large face of the grinding wheel needs to be on center line. So this creates the 0 degree rake angle geometry of this tool. And then we index 4 times, 90 degrees, and we get this funny little tool here that works marvelous. We're over at the tool and cutter grinder, and I already did the first one. As you can see, I'm just using a regular straight wheel. This one has relieved sides, but it doesn't matter for this course because I would rest the sides of the wheel anyways. And then I just come in here, I'm gonna clear the wheel, and I plunge in like this. And create the cutting edge up here. And also the clearance down here with the radius of the wheel, showing it here because it's on the back side. And do that 4 times, and that creates the even spacing. This gives a very, very, very aggressive cutting angle, of course. This is like about 40 degrees of angle between the clearance surface and the cutting surface, or the chip surface. It doesn't matter here because we're only cutting Torlon or plastic. I could grind a secondary bevel on this very acute angle, but it seems to work just fine. I still could come back if it didn't work out, put it back in here, indicate it parallel to the ways of the tool and cutter grinder, and try again with a secondary bevel that has a way smaller relief angle, but this seems to work. So here's the cutter. Okay, put it in here. I took the calipers and set the depth rod to a known dimension, or to the same dimension as the previous one, so I get a repeatable result here. Then I just touched off with the side part on the side of the wheel, zeroed out the dial of this movement, and ground 2 millimeters away, which is half of the diameter, so the cutting edge is on center. Okay, let's go. After grinding, I'm taking the 1.6 millimeter drill that I used to drill this tool, and I put a little bit of 1 micron diamond on it, really a small tiny amount on the OD. I'm using this in the bore, just spun by hand, to clean up the bore on these. Just to get rid of the burrs from grinding. If I wanted to do a really good job, I would probably turn a copper pin with 1.6 millimeter and use that to lap the ID, but I think this should do just fine. Just to clean up the bore on this. Diamond goes a long way. You really don't need a huge amount of it for such a small tool to lap. And yes, I'm also lapping the drill shank here. There is no embedding of diamond happening here. Both parts are very, very hardened. but there is rolling abrasion where the diamond rolls along. Here's the second one. On a good day I would do this on a lathe or with a cordless drill. I think this should do fine. So I did 3 of these tools, 2 identical ones, and this one has shallower flutes. Also means less clearance angle and less room for chips. Now that's the reason why I ground these so aggressive, to give the chip a little bit more room to make itself comfortable in there. We're over at the CNC mill and I just finished one of the contours of this part that I'm making. As you can see, the Torlon stock has almost like a tree, a bark. This is a 1 or 1.5 millimeter thick layer where the stock is a little bit harder than on the inside. That's probably due to the extrusion process or however this material is done. So I turned the stock down to 19 millimeters so it has a reliable diameter when I put it back in the lathe for parting off. And I took both ends and I milled the contour that I need onto it a little bit deeper than the final thickness of the part. Now we go to the milling machine and I will show you some magic in regards of this round pin feature that we need. Oh, and I also put the 0.5 millimeter key slot in here already. Just to change things up, I put the rigid table on the milling machine for no other reason than that I was using it to mill some stainless steel and I wanted to use flat coolant. And this table with the trough on the outside is extremely good at containing the coolant if you don't run large cutters at very high speed, which I didn't. This works extremely well. There is basically no coolant on the floor. It all goes down the drain, literally. I have my piece of stock in the grinding vise, in the tiny V block of the grinding vise, and I tighten the vise so I can still spin it back and forth. And I need that to align it vertically. I'm going to do that by just stacking up a few pieces. Just by putting these blocks here, which are all ground and square and parallel and whatnot, I can align this feature here to be vertical. You start out with it being at like this, then you slowly spin it until you make full contact with the block on the surface here. That's not a high precision way of aligning things, but it's, for this part, it's more than adequate. So now it's clamped vertically. Get my blocks out of the way. I need these again for when I do the other part. I need to do 10 of these, just to give you a perspective of how many I do of these. Now we need a edge finder. Using a regular 10mm shanked edge finder, but with a reduced diameter tip. This is a 4mm tip. Sometimes these are useful to touch off on very narrow features. So we touch off on this face. We can use the 10mm diameter down here because up here we have the key slot, and there is some danger of touching off in the key slot, and that would mess with our dimensioning. So we drop it down. We take 600 RPM. Okay, that was a lot of touching off. Get the edge finder out. Change the collet back to our 4mm collet. We could use the hydraulic chuck too, but I don't have a 10mm shank reducer sleeve for the hydraulic chuck, so we're using the collets here. The collets run very true too. There we go. Moving in position, stepping over as per drawing dimensions. Now the magic is just to plunge down, and this will leave the pin feature standing without much effort. And since all the material is still connected to the remaining stock, it's a very, very stiff and stable situation here. Okay, touched off on the end, but I'm going to use the quill because I have more, it's more sensitive in this case. Also, I'm using compressed air to blow the chips away to clear out the flutes. Despite having a fairly large flute because of the acute cutting angle or the acute clearance angle, there is still the issue of chips. Haha, and there we go. And there we go. This is almost too easy, to be honest. Apart from making a specialized cousin cool, this is really easy. This looks like a very surefire way to make a feature like this. Let's check the diameter just with calipers. So we get 1.61. The complete drawing is in ISO 2768 medium, means this feature has a dimensional tolerance of plus minus 50 micron. So we hit that. At this point, I don't even think I need a micrometer for this. This works comically good. As you can see, I got this nice pin feature on the end of this disc shape. So I got the question on Instagram after showing this technique and this approach, if this part couldn't be made out of two pieces, like gluing or pressing them together. And the answer is maybe. I don't know. This is a case of I'm making the part as per drawing. The engineer probably has done his research and has a reason to make it this way. I'm not in a position to question his design choices. I don't know the surrounding environmental effects on this part and also not the surrounding design. So who would I be to question his design? It can be manufactured. It's not a crazy, insane part. So I'm just making it per drawing and keep my sanity not discussing about something like this. This comes up each time I show a complicated part. This part is over-engineered or over-designed or over-complicated. And most of the time I think, do you know the surrounding design of the part I'm showing? Probably not. There is often a very good reason for what some people think is over-designing. Things are not even flat plates with holes. The world is a little bit more complicated, to be honest. We're over at the lathe, and I put the stock with the part still attached to it in here, touched off out here with the cutoff blade, moved over a little bit more than the final part thickness will be. Now I'm going to take a cut, then we check the thickness, correct accordingly, and then we part it off to final thickness. That's a weird geometry that we're creating here. So let's check the thickness here. Okay, we got 2.32. So we move over to our final dimension. And there it went. So I'm using a straight parting blade and this leaves this knob here. I could grind the end of this insert to an angle, but to be honest, it's no big deal. It's usually not a big deal on small prototype runs if there is a tiny little extra step like this. If this was a 100-part process, I absolutely would not want to remove the knob from parting off. In this case, meh, don't care. I have other things to worry about. I don't want to send another one flying across the shop, but I also don't want to break it off because I'm worried that I might chip a little part out of the edge of the part here. I'm just using a tiny hacksaw blade here. then break the final thickness off. Here we go. That's part for 1.6 millimeter shank, 0.5 millimeter, whoops, keyway slot, through hole. Pretty much done. Need some cleanup here with the parting off knob. Really a nice, reliable process, I have to say. And the whole strategy to make this part really works well. I'm very pleased. Here are the 10 parts finished. After parting off, clean up on some 400 grit silicon carbide sandpaper on a ground steel plate, and deburring with a scalpel. I also needed some 1.6 by 15 millimeter Torlon pins that I made with the same tool. I just plunged into a piece of the Torlon, cut it off, and ground the pins to length. That was a fairly simple part. And there's also 2 stainless parts, all backed up, ready for shipping. I hope you enjoyed. Thank you all for watching, and I'll be back.